All right, so now we're going to be doing a little bit of modeling. So our first example, example one, it's going to be competing species. Okay, and so suppose we have two populations. Okay, that's a abbreviation for suppose. Suppose we have two populations. Something like maybe rabbits and hamsters. So rabbits and hamsters are going to be competing for the same resources. And so we'll make some assumptions about our model here. One assumption. So in the absence of the other, we'll assume that each population is modeled by the logistic equation. You remember that? The logistic equation has a let me write down the logistic equation for us. That's y prime equals r times 1 minus y over n. Oops, forgot my other y. That's an important one. Okay, and so yeah, the idea here is that we have an upside down parabola in the y prime plane. Oops, sorry, that's y. And we have, this is the environmental threshold here, right? So we have y equals 0 and y equals n are the two equilibrium solutions. And 0 and n is going to be an attracting equilibrium solution. And 0 is a repelling equilibrium solution. Okay, so or unstable. Good. All right. So that's just general. That y right now doesn't, we haven't assigned any labels to anything yet. Good. Okay. What else should we assume? We will assume that the rate of change of the population downward, right, will be proportional to the number of rabbit, hamster interactions. Jeez. You're probably not going to be able to read that at all. Interactions. Alright, so there's going to be a symmetry going on here between the two populations. Let's see if we can build a model for each. Now, the general model might look something like this. So let x be the population of rabbits and y is the population of hamsters. Then our first assumption was that in the absence of the other, each was or had a logistic equation that represented the rate of change. And so how might we model that? We might say that x prime, for example, is alpha r alpha x times 1 minus x over beta, say. So that would be the first logistic model. And then our second logistic model would have some other variables in here, some other constants, alpha y. Let's say gamma y times 1 minus y over n. Good. Okay, and then also both populations will be decreasing in the presence of the other, and it's proportional to the number of interactions. So let's talk about this. Proportional to the number of rabbit hamster interactions. So suppose that we have a rabbit and we have a fox. Okay, well, suppose that we have lots of rabbits and one, okay, got lots of rabbits and one fox, right? So then how many ways can the fox interact with these rabbits? Well, we're assuming that there's one for each, right? And so if there was X rabbits and one, oh, wait a minute, we don't have foxes, we have hamsters. Uh-oh, how do you draw a hamster? Like that? Okay. Oh, whatever. Okay, so we have X times 1 number of interactions for one hamster, but then we have Y hamsters, right? So we're going to have X times Y is the total number of ways that we can get a rabbit and a hamster interacting with each other, right? And so if the decrease in the population then is going to be proportional to that, and so we can have a minus like k1 x times y and a minus k2 times x times y. Okay, and so this is what's telling us we have a competing species model, is that these negative signs mean that the population is decreasing because of the number of interactions. Okay, so that would be the competition part. Good. Okay, so let's ignore my drawing here and let's just take an example of what we might see in a competing species model, and then we'll try to solve it. So example, well, be more specific. X prime is equal to x minus x squared minus xy, and y prime is equal to 3/4 y minus y squared minus 1/2 xy. Okay, and so how do we do our analysis of a nonlinear system of differential equations? That's right, it's the two-step. The two steps being solve for equilibria, and then the second step is to linearize and use Poincare to classify. Good. So in solving for our equilibrium solutions, let's say we'll have x times 1 minus x minus y equals 0 in the top one, y times 3/4 minus y minus 1/2 x equals 0 in the bottom. Right, so from the top we see that either x equals 0 or x equals 1 minus y. Okay, and now we plug each of these into the second equation. So if x is equal to 0 on the top, we have y times 3/4 minus y equals 0 on the bottom, right? Or we have y equals 0 or y equals 3/4. Okay, and so notice that we just have 0, 0 and 0 3/4 now, right? Good. Now, what happens if x is equal to 1 minus y in the first equation? Then in the second equation, let's see, this is our second equation here. Y equals 0, or, I'm going to run out of space. We have 3/4 minus y minus 1/2 times 1 minus y equals 0. Okay, so notice, by the way, that this number gives us, what is that, 1, 0 as a solution. And then figuring this one out, what do we get? 3/4 minus y minus 1/2 plus 1/2 y equals 0. I believe this simplifies to 1/4 minus 1/2 y equals 0. So y is 1/2, and then x is also 1/2. So now we have 4 solutions. Good. And now with our 4 equilibrium solutions, we construct our Jacobian matrix. In fact, maybe I'll pause here. I hate to stop in the middle of an example, but in this case we're already out of time, so I will keep going on the example in the next video.